Jim, do you remember when we were talking about x-rays not too long ago?
Yes, I do remember that.
Well, have you ever wondered about MRIs?
Yes, I have wondered about MRIs.
Well, MRIs are very chemistry heavy, but I have never taken a specific class in MRIs. So I thought it would be a good idea to get an even expertier expert to come and talk to us about MRIs.
Nice. Where will we find someone like this?
Oh, actually, I have someone right over here.
Whoa.
Claire, we're bringing back our probably the most popular guest ever, Claire.
Yeah,
welcome back.
Hi.
So are you ready to teach us all about MRIs?
Oh, yeah, you bet.
All right, let's do it. Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Claire Caballero edition. What up? Did I say your name right?
Yeah, you did.
Okay, so for those of you who've been listening for a while, we've had Claire on as a guest before. But Claire, why don't you quickly remind our listeners what your background is and why you're even qualified to teach this topic?
Yes. So, yeah, like Melissa said, I'm Claire Caballero. I'm a PhD candidate at UNT Health Fort Worth. We actually just changed our name, so it's not as much of a mouthful anymore.
Nice.
When I came on
like
2
I still
years
go to
ago.
the same school.
Yes, but different name. Still in Fort Worth, so that's fun. And I'm a PhD candidate in pharmacology and neuroscience.
Woohoo!
So my research focus on the cells that line the ventricles in your brain, which are cavities where the cerebral spinal fluid is held. That's all I'll talk. That's all I'll talk about it.
Wow.
It's kind of convoluted, but really fun. I really have a good time with it. And this past semester in the fall, I took a class called neuroimaging. But basically it was a class about MRI. So I got to learn all about how MRIs work. Do I understand fully how they work? No, and you'll know why, because it's actually quite complicated. But it's really cool. So I fell in love with MRI preparing for this episode as well. So
nice.
I'm really excited.
And I want to interrupt and say what a PhD candidate is.
Yes, please.
So a lot of times in grad school, you start out and there's like a set number of things you have to do before you can get your PhD. But usually it's kind of in phases. So there's often classes and then there's often special exams that you have to take that can be over any variety of things. They can be written, they can be oral. There's all kinds of exams that different programs have, but they basically are designed to test that you know enough to be able to get a PhD in this area. Yeah. So Claire has passed those exams and is mostly done with her course requirement. I think there's just a little bit of her courses left. So basically all that stands between her and her PhD is finishing her research. So she's super trained. She knows a lot.
Yes.
So we're very excited to have Claire here. And I think I maybe was... Whenever I started the podcast, I was a candidate, technically, I think, or in that. Maybe I had been a candidate for OChem and then we switched over. So we definitely trust Claire. She has so much knowledge. So
yes, and I actually also do MRI for my research. So I can talk about that at the end too.
Okay, great.
Nice.
So I'm really excited.
Me
but actually,
too.
Before we get into MRI, I'm actually going to talk about something else.
Okay.
Called nuclear magnetic resonance, or NMR. That's how I'll refer to it. Have you ever done an NMR experiment before? I've never done it. I also hated looking at the graphs when I was in OChem.
Yeah.
It was kind of convoluted, but I just don't think it was explained to me very well. So now now that I know, I think I would like it more.
Well, I actually just gave a test on NMR today.
Really?
Yeah. It's more on the interpretation of the graphs. But when I was an organic chemist, we basically... That is something that we use to be able to tell, like, oh, did you make the molecule you think that you made or not?
Exactly. So, yeah, it's really about how looking at structures of compounds, especially like things that you're making yourself.
Huh.
So, in order to talk about NMR, we're going to talk about magnets because you probably heard in the names, it's all magnetic.
Yes.
So, have you guys talked about like protons and electrons? I'm sure you have. Of course.
I think we have. But I don't think it ever hurts to kind of do an overview of like, okay, there's charged particles, basically.
Right. Yeah. So like an atom is made up of its nucleus, which has a proton, which is a positively charged molecule, and then a neutron.
Or a positively charged subatomic particle.
You're right. It's not. Yeah. I'm so far removed from chemistry and physics that I just think of everything as
That's okay.
molecules.
I actually mix up
Subatomic
molecule and atom a lot.
Yeah.
I want to say the opposite when...
Atom's like the smaller one. Right. Yeah. Then there's a neutron also in the nucleus. And it's called a neutron because it has a neutral. There's neutral charge, nothing. And then electrons occupy shells out. They basically just orbit the nucleus outside, and those are negatively charged. So you can forget everything that I just said except for protons.
Yeah.
Okay.
Protons are the ones that we care about. They're positively charged. And since they're positively charged, they generate an electromagnetic field in itself, which is really cool. And that's the principle. That principle is the basis of our NMR. So whenever you place something that has its own magnetic field into a larger magnet with a larger magnetic field, that proton does something called precessing, I think is how you pronounce it. Basically, it's wobbling. So protons aren't static. They do move. So do electrons. And so when you put it into this magnetic field, it starts to wobble, and it aligns with the larger magnetic field that you've put it in because it likes to do that.
Okay.
It's like, oh, I found a place that I like to be, so I'm going to align with this magnetic field.
Like a compass likes to align with the Earth's.
Yes, perfect. Perfect. That is so.
That's a really good. I was trying to think.
So good.
What's a good analogy? You came in hot.
Yes.
Good job.
Yes, that is. That's exactly what it is. So then, in the machine where you've put your sample, a strong electromagnetic pulse is applied. So that's called a radio frequency pulse or an RF pulse. And basically what that does, it forces the proton to go out of the alignment that it's in.
Okay.
And it does that for as long as that force is applied, as long as that pulse is applied. Well, the proton doesn't like to be there. So as soon as the pulse is off, the proton will start to spin back into its alignment with the magnetic field. And when it does that, it releases energy. And when that energy is released, it's picked up by the scanner, by the machine. And that is where we get our data from in an NMR.
Whoa.
Yeah.
Weird.
I know. Isn't that weird?
Yeah.
Who figured that out? I needed to look. I should have looked up some history because I don't even know how you like even know that like protons do that in the first place. It's
Yeah.
Can I ask some questions?
Yes.
When the magnetic pulse is applied that makes it go out of alignment, is it flip in exactly the opposite direction, or is it just like out of alignment?
So you can actually change like how it like out of alignment it goes. Normally it goes perpendicularly, if that makes sense. So if like the magnetic field is right here, then the proton goes up like this.
Okay.
And then it spins and rotates back down into alignment.
And it's releasing energy when it goes back.
Yes.
Is that because did it absorb energy from the radio frequency?
Yes. I'm pretty sure.
Okay. I'm not 100% on that because this is deeper into the theory of NMR than I've gone.
And that's definitely like quantum mechanics based, which is like I took a quantum mechanics class when I was in college and it was crazy.
Yeah.
It was crazy. I'm like, wow. Like I felt really smart because I was like, wow, I kind of get it, but I felt smart for kind of getting it.
Yeah.
Right.
I saw Ant-Man.
So I mean, basically, you know everything.
Yeah, I got it.
I got a
Totally
B
got it.
in physical chemistry 2, which is quantum mechanics. And I have never worked so hard for B in my life. I took a whole week off work. I like waited tables in college. I took a week off work. I gave up all my shifts. I sat outside my professor's office every day. I've never worked so hard. And I was so proud of that.
You should be, because it was so tough.
It was so hard.
The only reason I got an A was because my professor knew how hard it was. So he made all our exams take-home exams. And he told us, he was like, you can look up anything. You can literally use the internet. The only thing you can't do is post the questions on Chegg or on Quizlet for people to look at. or for people to answer for you. He said, I will be looking.
Yeah.
But he made them take home, and we did like projects and like presentations.
Nice.
So it was more like you should understand the principles, but it's okay if you don't really know how to apply it, because I'm like, I've never used it until this class.
Yeah.
Where my professor was trying to kind of get us to understand the principles of quantum mechanics, because that's his specialty.
Yeah.
And I was just kind of lost. But you don't really have to understand it to understand the protons moving and stuff, which is really nice. It's just understanding that the energy that's released, that's what the machine is picking up, and it's able to like encode what's going on.
Okay.
Yes.
Great. I'm tracking. Thank you.
Jam, are you tracking too?
I think so.
Okay.
I think at a much more pedestrian level, I am tracking.
Well, I also have another analogy that also my professor gave me, which is really nice. So it's like a radio, which is also nice to think of because it is actually a radio frequency pulse. So it actually is very much like a radio. But you can kind of think that the pulse that's given is like the radio waves. They are radio waves. And the protons, when they're getting out of alignment, that's like them receiving the radio waves, kind of like how a radio like takes in the current, or not the current, but the wave. And then the protons going back into alignment is like a speaker transmitting out the sound, which is like the data that's generated.
Oh, I see.
Nice.
That is really helpful. Okay. Yeah.
So it's like a radio. And it's hard to say, it is a radio basically. It's just instead of sound, we're getting like a different kind of data. So now we can get to the star of our show. So can you think of just a very simple atom that is found everywhere that we could use for NMR? And the hint I have is that it only has one proton. You think of
I can't answer this because I already know. So it's all on you, Jam.
It only has one proton?
It only has one proton. It's on the periodic table.
I mean, is hydrogen the first? Okay.
Yes, it is.
I was like, I feel like that's the one that has one electron and one
proton.
Proton too?
Yeah.
Okay.
Yeah,
nice.
and it doesn't have a neutron.
Isn't that weird?
It just, it doesn't have a neutron. So it's literally just a proton. Like when in NMR and MRI like experiments, the words hydrogen and proton are used like they're just used together because it doesn't really matter. Like they're just a proton.
Okay.
It's just a proton. And they're literally everywhere. They're like attached to every single molecule, basically. Every single other atom always usually has a hydrogen attached to it. So just sheer abundance makes it really easy for us to be able to tune in to the frequency that hydrogen is at so that we can look at how it's behaving.
Oh, interesting.
Yeah.
And I'll chime in with an organic chemistry perspective is like, organic chemistry, the foundation of that is carbon. Carbon likes to make 4 bonds, but it doesn't usually like to make 4 bonds to like any old atom. It wants to usually make 4 bonds with hydrogen or one other carbon or 2 other carbons, and hydrogens just fill in the gaps. And every once in a while, it'll have like an oxygen or a nitrogen, but almost every organic molecule, which is what we're made up of, has carbons surrounded by hydrogens as the base unit. That's like the starting point. All of our proteins, everything has that.
Exactly. And like water, that's just oxygen and hydrogen as well. And so, that's literally what I was going to say. Like hydrogens, they're everywhere, but they don't exist freely. And so...
Sorry, I didn't mean to scoop you.
Oh, no, that's great because you're the OChem expert here. So I would actually needed your help. Different chemical environments. So it's like, think of like a hydrogen being associated with an oxygen versus it being associated with like a carbon. That changes how the protein like behaves inside the magnetic field. And it causes it to give off a slightly different like signal in the machine. So that's how your chemists are able to predict these structures. It's like, I know when the data, like the graph, so NMR generates peaks. I don't really know what the peak is. I guess it's the energy. Do you know?
I think it's the energy. Like they basically look at, how much energy is required for this to get back into resonance. Right. And if the hydrogens are in one specific environment, if there's like 3 in one environment or something, they will all appear in the same area. So
exactly.
Every unique hydrogen gets its own little peak.
Exactly. And so you can be like, oh, this hydrogen is going to be associated with the carbon because it's behaving like this and it's peaking right here on the graph, versus this hydrogen is going to be associated with an oxygen because it's behaving like this. So that's how chemists are able to predict what the structure of whatever molecule they're wanting to look at is.
And I'll say we've talked about functional groups a lot on here. And that's just basically groups of atoms that, so hydrogen and a carbon and an oxygen, all three will hang out in this specific arrangement and they'll consistently act in a certain way. And in NMR, which is looking at these hydrogens and looking at the structure of the molecule, based on the functional group, you can kind of expect certain behaviors. Like, oh, this is a functional group I expect to see. And I know that in NMR, this functional group acts this way. So we can use those like little building blocks to give us clues about the molecule.
Yeah, exactly. So I still am really bad about reading NMR like graphs. So when I started to take this class, I was not really looking forward to it because I just never, like, that was my least favorite part of OChem. I'm going to have to be honest. It was awful. I just never, like, they would be like, okay, here's NMR. Like, what structure is it? I'd be like, I don't know. I just see little peaks. I'm like, it could be anything. I guess. I don't know.
That reminds me of, like, in The Matrix. Have y'all seen that movie? Okay, good. You've seen it. You know of it.
I've seen it. I don't remember a ton. And
Yeah.
I think I've seen it multiple times because multiple times I thought I'd never seen it.
Right. That's not, yeah, it has that effect on you, you know?
Yeah.
But there's the part where, like, he's talking about how they're looking at the code of the Matrix, you know?
Mm-hmm.
And it's like, obviously just all these symbols. There's not even exactly numbers or letters, like kind of different, like streaming down the screen.
Yeah.
And he's like, how do you know what you're looking at? You know? And he's like, oh, at this point, you know, when you looked at it enough, you just see, and then the joke he makes, he's like, you just see like brunette, blonde, redhead. But like what he really means is like, it just looks like data.
Yeah. Yes.
But it's interesting that the way you're talking about the NMR graphs is like it being like, this is hard to read. But then for people who've maybe done it for decades, it's like, oh yeah, I know exactly what.
Brunette, blonde, redhead. Yeah. I'm that guy in this scenario. Yeah, I know. And it is hard. I like try to explain to my students and they're like, well, how do you just look at this and know what the structure of the molecule is like? And I have to think, how do I do that?
Yeah.
What do I do
Right.
for that? And a lot of it is just practice.
Yeah.
It is really challenging, but there's some things you can start to expect. And sometimes it's still hard for me, even after all this time. So
Yeah, and honestly, like one thing I think I found is that I'm not a huge like visualization person. It takes a lot for me to visualize something in my head. Like it like requires me to work. I'm not like one of those people who are like, I don't see anything in my head. I know there's some people that are like that. But it like takes a little bit for me to like work. So I like when I see a structure or like I see like a chemical formula or something, like I don't see the structure in my head. I have to like get it on a paper. So I'm like NMR, I'm like it could be anything because I'm like I don't see it in my head. And maybe I just didn't practice enough either. So that could be it. And I don't have to practice. So I'm just out of it basically. Okay, but yeah, does that make sense? NMR makes sense.
I think so. I mean, we'll find out, I guess, what holes are there in my understanding.
Right.
should we do a check-in where you try to summarize it before we move on since it kind of builds?
Sure. Yeah, we can do that. I'll let y'all decide when that's good and worth it to do and when it might be like a detour kind of thing. But I'm happy to do it now.
I think now
It'd probably be helpful to me.
Yeah.
It'd probably always be helpful to me. So I'll let y'all decide.
Okay.
Yeah. Obviously, I have people who are watching who might be like, come on, all right. You know. So the proton wants to, we're talking specifically about the proton and hydrogen in terms of detecting this. But in general, I guess protons want to be aligned in whatever magnetic like sort of field that they're in.
Mm-hmm.
And an NMR creates a different field temporarily.
Yeah, I would say it's like a pulse.
A pulse.
Is applied
Okay.
that knocks the proteins away from the magnet.
Isn't it crazy how quickly like details fade? Like as soon as you started saying that, I was like, that's exactly what you said a moment ago. But I just was already gone. So it creates a pulse that knocks it out of its the alignment it wants to be in. And then as it comes back in to the alignment, kind of like shaking up a compass and then stopping, it would find its balance back. As it's finding the way it wants to be aligned again, it is releasing energy that is able to be picked up by, like, the NMR is tuned in a way to pick up what's going on there frequency wise.
Yes.
And because hydrogen being detected in all these different places is not just by itself, it'll be with other things like carbon or oxygen or whatever. What it's bonded to when it's under this pulse thing that knocks the proton out and then it comes back in and it's being detected, you can tell on the graph what situation this hydrogen proton is in because of the way it looks on the instrument that's tuned to whatever.
That's like literally it. That was really good.
Okay.
That was really good.
Great. Yeah. That was a really good
I mean, this is like a
explanation.
hard concept to like, it like took my professor like several classes to be like, this is what like the thing does. Because we went over NMR first.
Yeah.
Because surprise, surprise, MRI is just basically NMR. It is NMR.
Surprise,
actually.
surprise.
I actually found out today when I was like prepping for this that they changed the name of like, I was like, why isn't it just not called NMR? Like, why is it specifically magnetic resonance imaging? That's what MRI stands for. And it's because when MRI started to like come about, it was like the 70s, and NMR was discovered in 1945 actually.
Whoa.
So nuclear stuff was great. Like people were so scared about nukes, like nuclear energy, nuclear bombs. And so when people heard the word nuclear, even though it's just talking about the nucleus of an atom,
right?
They just freaked out. So they're like, okay, let's just shift it to magnetic resonance imaging to make people feel more comfortable.
So NMR, say it again. NMR was nuclear
magnetic resonance.
Okay, so it was called that, and what probably would have ended up being what MRI was also called in that particular use case.
Yeah,
but because of
people being scared.
Cold War, all kind of stuff.
Yeah.
They decided not to call it that NMR.
Yeah. Oh. Even though we still use.
Oh gosh.
They don't call it that anymore. NMR.
I just didn't even notice it. What that sounded like.
It took me a second.
Really bad. That's why.
No, it was good.
That's why you didn't understand it, because
it was good. I was also just excited to tell you the chemistry fact that the resonance is like it resonating with the magnetic field, right?
Exactly.
Were you already going to say that?
No, I wasn't going to say that because I didn't know. I was like, could I explain that well? I didn't know if I could do it.
It's like when it lines up, it's right?
Yeah.
Okay.
Yeah, exactly. Yeah, the pulse that like we're giving to the proton is at the same frequency that the proton resonates at.
Okay.
And actually, we can actually kind of go back to NMR. You don't have to do NMR just on hydrogen protons. You can do them on any proton. You just tune the pulse to whatever frequency the other protons are resonating at. A common one is carbon-13. That's an isotope of carbon. It has an extra neutron, I'm pretty sure.
I can literally, this has come up already on this episode, I can literally never remember if isotopes have extra neutrons.
I think it's an extra neutron.
I think that sounds right, but
What's
for
the
some
other
reason
one?
I can never rember.
Proton.
I mean, what's the isotope and isomer, or what's the other thing?
Yeah,
Okay.
isotopes and isomers. I think they have to be odd numbers. Like like carbon has 1, carbon-13 is 13. Hydrogen has 1. You have to have an odd number for it to work.
Oh.
Yeah.
Yeah, and the reason that is because the way that protons are, they have what's called like a magnetic moment, which means their magnetic field is like in a certain direction. So it's like we chemists, physicists call it either like up or down. That's also called the spin. I don't know if you guys have like talked about that before. Basically, it just has like a moment kind of thing. And Melissa, we were talking about this beforehand. She had a really good like visual where I guess if you're listening to this, you can't see, but it's like almost like
I can describe it.
Yeah.
So if you curl your hand, like you take your 4 fingers and curl it like you're going to make a fist, but don't put your thumb down. If you curl it to the left, your thumb will point up if you're using your right hand. And if you curl it to the right, you have to flip your hand over to do that. And your thumb points down. And that's how we use like electrons create.
Yes.
magnetic moments also.
Yes. So electrons do the same thing, but it's negatively charged. Protons do the same thing, but it's positively charged. And that's getting into quantum mechanics and everything. That's like a very quantum basis thing. But basically, I wanted to say that if you have 2 protons, they cancel each other out.
Yeah.
So that means one spin is up and one spin is down.
Yeah.
So the net like magnetic field is usually 0.
Got it.
So that's why hydrogen is so nice. It only has 1 proton. So it has a positively net magnetic field and magnetic moment. So it actually has something that can be altered by this larger magnetic field that like you're putting onto the proton. So that's why like carbon-13, I think there's like oxygen-17. I know that because we were trying to see if we wanted to use that for our MRI experiments. But it's like really expensive. It's like $3,000 for 5 grams. I know that's such a random thing, but I found that out today.
Wow.
It was so, I was like, I have to tell somebody.
5 grams is so small.
Yeah.
That's so interesting too. There's things like that where you just know that like, oh yeah, there's not this insane market for it. And it's also like probably hard to make. I mean, it just, that's so interesting.
Yeah.
Hard to isolate. I don't even know if we can make
Oh,
it.
I see.
Yeah.
Right.
You just have to find it and purify
Probably,
it, I think.
So that's probably why, because it's like, how abundant is it? It's probably not even.
I think isotopes exist at like 10% of the rest of.
I had like, one of my sources has a table of all of these different like isotopes that you can use. I'm sure there are abundances on there too. I remember having to do all those calculations and stuff too in like Gen Chem.
Interesting.
Because like normal hydrogen, for example, weighs 1, but if you have an isotope of it, it'll weigh a little bit more. And so that's why hydrogen on the periodic table isn't just 1, it's 1.008.
Yeah.
Or like carbon is 12.0 something, like small number, because there's some carbon-13. And so like
I see.
these the isotopes that exist in the world make the net average of carbon like overall is not exactly 12. It's a little bit more.
Yeah, it's very. That's actually in our lab. We're currently using an isotope of water. It's called deuterium or heavy water. But
We have
basically,
talked about this.
Yeah, you just add a neutron into, or it is and a neutron is in the nucleus. So we're actually using that in my lab right now. It's really interesting. That's not as expensive as the 17 oxygen isotope that I was investigating.
And if you want to take an NMR in a chemistry lab, you always have to dissolve your stuff in a solvent. And the solvent has to be that isotope version where there's, instead of hydrogen, you've replaced it all with a heavy hydrogen. So basically a deuterium so that it won't get picked up in the signal.
That's literally like what we're doing right now in the MRIs. We're like trying to see if like the deuterium, like how it picks up on an MRI, and it doesn't. Like the whole purpose of it is it does not show up on the MRI because it resonates at a different frequency than water does. So if your MRI is tuned to water, then then the heavy water won't show up because it's not the same as like normal water. Anyway, that was a tangent, but it's a good tangent. It's a fun tangent. Yeah. So
and as long as you're tracking Jam, I feel like what's harder about this episode is normally I'm like, okay, it's just me and you here.
Yes.
But now it's like me and Claire, and I know a little bit more about this than a lot of times in,
Yeah, and y'all could like go off on a science, journey, and I'd be like, okay, see you guys.
But do you feel like you're tracking?
Yes, I think so.
Okay, perfect.
Okay, great.
Well,
also, the spin thing, I don't know how much that matters a lot. I don't know why it came up, but it has come up. I've seen you do the hand thing. Like as soon as you did that, I was like, my brain
it's
is
like
telling me.
grabbing like a mug almost, but
my
your
brain's
thumb
telling me
is
that you've explained this to me before for some reason.
Yeah.
I don't know what episode it would have been, but
it is huge in electrons and it's huge in protons too.
I only think of it with electrons. Yeah. That's why electrons are represented as arrows.
Yes.
Because they make magnetic moments.
Yeah, exactly. But yeah, I get the spin. The only thing that's important is that helps it make it the magnetic field. Like that's what's important for making the magnetic field. But you don't need to remember that. You just need to remember that protons do have that.
Okay.
So yeah, now we can go back to MRI, which is just an NMR. MRI and NMR basically, they are the like exact same like physical, like physics is going on. Same physics, same chemistry.
Okay.
So yeah, it's just an NMR experiment using the human body. So it's like, what do we have an abundance of, like in the human body? Like, what are we 70% made of?
Water.
So, and water has 2 hydrogens, and there's tons of hydrogens in other molecules everywhere else in your body.
Yeah.
I found a fun fact: 63% of all atoms in your body are hydrogen atoms, which makes sense when I think about it. But like, that's still like, that's like more than half of all the atoms in your entire body are hydrogen atoms.
That's crazy.
Yeah, that is crazy.
It makes sense because it's like, well, if we're 70% water or whatever, that's all of those are 2/3 hydrogen when you go to the number of atoms.
Right. But like when you say that out loud, it's like, wow. So
we're more than half hydrogen.
Yes. Yeah. It's yeah. But when we think about carbon a lot, but it's like, no, hydrogen's like the main player.
Yeah, that is crazy.
Yeah.
So MRI, just takes definitely takes advantage of this fact, because there's just water everywhere, and that's why like we can use MRI for like soft tissues instead of like an X-ray where you can't really see soft tissues, because hydrogen is in both fluids and like fat and tissue. Yeah. And just like in NMR, where like the hydrogens act differently when they're in different environments, they act differently in different types of tissue in an MRI, like for an MRI experiment. So like protons that are just free floating, like in your cerebral spinal fluid, or like in bile or something, like just in a fluid, act differently than the hydrogens that are in like muscle or fat or ligaments or your brain or anything like all of those act differently. So that's how we're able to get the contrast that we're able to do in the MRI.
And that kind of makes sense to me because like an acidic proton that is like floating around in a solution like bile that's maybe disassociated is going to act differently than a hydrogen that's bonded to a carbon in like in a solid carbon bond. It's not just floating around by itself.
Exactly.
So that makes sense that they would show up differently.
Exactly. And it's like even different tissues act differently. This is getting a little more pedantic, but like in your brain, you have what's called white matter, which is like bundles of axons. And axons are like the really long parts of neurons where like the electrical signal goes. So that's called white matter. And it's called white matter because it looks white. It's wrapped in like fat that like insulates, that makes electrical signal go faster. And then there's gray matter, which is just where all your cells are. And the hydrogens in those 2 types of tissues act differently as well. So on a like brain scan, which is like all I look at, I just look at brain MRIs all day. If I'm looking at MRI, those will look different depending on the MRI image that you're looking at, but they always look different. It just depends on if it look brighter or darker.
Are we talking like really subtle like differences in terms of like the machine's tuned to pick up on that really well, but like are we talking that these differences are like, just as it's going back into the position aligned with magnetic field it wants to be, it just happens to do it just a little wobble this way or that way, or like like what are we talking?
It just depends on like the limitations of your machine or like how you set up the sequence of the MRI. Like there's so many different parameters that go into like how you set up the different like radio frequency pulse. There's different properties of the MRI that I can get into that are just like for example, like whenever the protons get like unaligned, I guess, and they go back, one of those properties is called a T1, which is how long does it take for the proton to get from here to here. Okay. And so like protons in free water take longer to do that than they do in tissue. And so if you take a T1 image, the fluid will be dark and then the tissue will be bright. Got it. Okay. So it's like the more free water there is, the darker the image will be. The darker that part of the image will be. Got it. So it can be sensitive. Yeah. But if you like, you just have to tune what you want. But I will say spatially, the resolution, you can't really get like super duper small. Like you could get to like, I'm trying to think of like the like actual size that I forgot. Like, for example, the cells that I'm really interested in that I do my research on, they're about 10 microns like thick, and the MRI cannot pick that up. Interesting. So it's not spatially encoded.
Can you compare that to like a width of hair?
Yeah, probably
Is it how big?
I don't know how big.
Like how big is a micron compared to a width of hair? Because I feel like it's a fraction of even a width of a hair.
I'm like, how big is a width of hair?
I don't know either. Rats, I thought you might know.
I don't know. I'm like, I don't even, because I just think of in terms of microns every day. But it's like tiny. It is so small. Maybe like the eye of even less.
It
like
would be
way
very
less
small because it's microscopic,
right? So it's like you can't see individual cells a lot of the time on MRI. So like spatially, you're not able to see unless you try to like code for that, like in your parameters. But sometimes there's just limitations of the machine itself that it can do, depending on like the strength of the magnet itself, how big it is, like how big the MRI machine is. Are you able to get everything in there in the image? So there's a lot of different ways that I just don't really even understand. That I'm like, how are we changing this and fixing it? To like generate the image. But I know that it can be done, but there is limitation. Like that's something we're trying to figure out in my lab right now. That we're like noticing we have some limitations to what like our MRI can do. But we're trying to like figure out, can we change the like not change the actual hardware, but change how the hardware operates so that we can see what we want to see. That makes sense.
Can I ask, this is maybe a weird question, but something that I've always struggled with is like, okay, I understand the technology behind an NMR. And I know I can put a sample in this big giant magnet. Literally, we drop a sample into a giant magnet. And then it sends those impulses, it picks us up, and it generates, the graph of like, okay, here's where energy, we looked at that. But I have trouble knowing how NMR turns into MRI. Do you have a good way of summarizing that? Or
well, do I even know? That's the question. I don't think I do, because that's the part I still really struggle with. It's like, how do we get from like this release in energy creates an image? And it's like even Googling that like question doesn't really give you easy answers, because most people like on like Reddit, because even I trust that a little bit more than like the generic clinical MRI, because those are geared toward like, oh, like these are just people that never don't even know what MRI is. And even on Reddit, people are like, oh, like this is a really, really complicated question.
Wow.
And it takes a lot of math behind the scenes of coding.
Right.
But what I think, like what I understood from like my class, so like need to look at my notes, I know it definitely has to do with the location of where the proton is. So it's a lot of spatial encoding. And I know there's something called the K space. I don't know what the K means, but I know that like if you're in the middle of that K space, like where the proton is, that gives you like the most signal, and that gives you kind of like the like area, the shape of what you're wanting to look at. And at the edge of that space gives you the contrast. So like where there's like edges and stuff, like edges of structures and stuff like that. And if you can make your sequence the way you want it to, you can get a lot of contrast between like different parts of the brain or wherever you're looking at.
Okay, I think something just clicked. Can I try to say what I think I just understood? So for me, I'm looking at a bunch of one type of molecule.
Yes.
And so it's easy because it's like, here's a vial of one type of molecule. So like let's say we're looking at ethanol. I just put a bunch of ethanol in a tube and I'm only looking at that one molecule. But I think what you're saying is for MRI, it's saying I'm looking at this one area and the one molecule in this one area, or the type of molecule in this one area. And that gives me information about that area. And then the computer takes that and says like, okay, so this is what we're seeing in this one area.
Right. Yeah. So it's very spatially encoded. And I know that like
helps.
Like, so this is something else that I know that I'm like, I don't know how it does it, but I know it helps. That like, so there's one magnet, right, in the MRI that makes the magnetic field that the protein's like aligned to. There are other, we call it like a coil, like it's inside a coil. So basically the coil is just like the giant cylindrical object that you're placed in. There are other coils inside the machine that generate other like currents that help with the encoding of the spatial information.
Wow.
So it's like, and there's ones that go in the X direction, the Y direction, the Z direction, the ones that go in like the XY direction, the ZY direction. So it's like, and you can like, and those can be changed too. And actually that's where the noise is coming from, I'm pretty sure, for an MRI. Let me double check on Yes, so that's like the knocking noise that you hear in an MRI. Those are called gradient coils, the ones that are helping encode that spatial information. Those have to be turned off and on all the time, so that's why you hear like that knocking noise on the MRI, because they're being turned on and off. So that's why an MRI is really loud.
Yeah.
So you have these magnetic, basically, fields that are fighting with each other.
Yeah, so you can like get all the information that you want out of it. Yeah.
That's so interesting. I feel like there's something there about like, obviously it's much more complicated, but there's something there about like, we've talked about the difficulty of understanding like a picture, for instance.
Yeah.
And like we've done the film episodes, but if you take the digital version of that, where it's like, okay, really it's not a picture. It's actually a bunch of information.
Yes.
And when you open it, because our phones and computers and stuff like that have been taught how to read that, it says, okay, it's this long string of data, and I know that what this program has been taught how to like put that into showing you this pixel will be this color and this level of brightness or not, and the next one will be this. It seems like what you're saying is somehow all the data, which is in like, you know, number form, they've figured out how to then be like, okay, now we'll take that and we'll render it into a like, okay, the value of this little part of the image is going to be dark because of the number from the whatever.
Right.
And it'll be whatever the K space and how contrasty or whatever. And where do we put it in the picture? Because we're having to figure out spatially, like, where do we pick up on this one? And, and that somebody, many people or whatever probably figured out how to get from like the graphs I was talking about earlier with the NMR to like what does it look like to have like a 3D? Or whatever.
Yes, exactly. Like that's exact, because like that's what the computer is doing. Whenever it's like there's so much math behind the scenes that like I don't understand. I'm like, maybe I could understand if I like spent like a couple months trying to like delve into it. And I'm like, would I even still understand it?
Right.
But like that's such a good analogy, is like a digital picture, because it's actually quite similar. You do generate, we don't call them pixels in MRI, we call them voxels. A voxel is just a 3D pixel. So instead of having like a pixel is just a 2D, it has like a length and a width. A voxel has like a length, a width, and a height. Like it has 3 dimensions because you're able to get 3 dimensions in an MRI. So it is pretty much exactly what you're talking about, where it's like, no, you're not really taking a picture, you're just getting all this information to make a picture. Like the program, the software is able to do so. And like behind the scenes. So that's a really good analogy as well.
Yeah. And I think what's helpful is the 3D, you clarifying there's a 3D nature to it, that it's like able to pinpoint like, okay, right here in space, I'm getting this signal, and then move over 1 micron and I'm getting this signal. And like, so that's helpful, because I guess I think of NMR almost in like a one-dimensional thing. It's like we have one molecule that's taking up all the space, and we get one signal for the one molecule, or like, you know, a set of signals that goes with one molecule, and it's one chart. And so I was having a hard time thinking like, but how does that translate to a body that's full of so many different molecules all over?
Right.
And
no,
so
and that's like,
helpful.
like when you're like, when I'm doing the MRI, like, and I have the software open, I have like, there's like 3 different images, and one is like you're looking in the X direction, one's in the Y, and one is in the like Z direction.
Wow.
And so like you can like look at, it's like, okay, which one do I actually like care about, like that I want to see? And like I can either ignore the other ones, or I can make the other ones do what I want them to do, so that this one specific image is really nice, because we can't, it's hard to look at 3D images. And sometimes we just don't even really care about those like types of images when we're like trying to see what we're looking at. So I'm glad that, so 3D, it is 3D.
Wow, that's crazy.
Also, I did a very quick Google search, and according to the quick Google search, 1 human hair is 70 microns.
Yeah, so a 1/7 or almost like a 1/10 of that. So it's like 1 voxel in an MRI will contain hundreds, if not thousands, of cells inside of that. And you're not able to see cells, but it's helpful for seeing other, like all sorts of stuff. So
wow.
Dang, any questions? I don't know if I can answer them. But do we have any questions at this point? Really, I guess the principle that you need to know is that like hydrogen and protons act differently in different types of environments, and that is what's able to generate like the different contrasts that we see. Yeah.
That's crazy. It's like y'all mentioned this earlier too, but the fact that people figured this out, it's like this switch is already happening.
Yes.
Right. But then us being like, well, we can mess with the magnetic field and then watch what happens afterward.
Yeah.
And detect that.
Yeah.
It's just so weird.
Yeah.
Like, and great though.
Yeah.
I mean, the number of things MRIs can do and detect that it's like, you're talking about brains a second ago. It's like, you don't want to open up somebody's head.
Yeah.
If you don't have to, like, you just don't want to do that. And and there's so many, it's better now, but even still, it's like, you're going to avoid surgery at all costs.
Yeah.
If you can do other things first.
Yeah.
It's like, we do not need to lay our eyes on the tumor or the broken thing or whatever in the case of like an x-ray. It's like, we don't need to do that. It's better for things to stay closed up and not risk infection and whatever other problems and stuff like that. And so it's just crazy the ways we figured out how to see stuff.
Yeah.
When we did like a very, we talked about x-ray not that long ago. And I was like, that is insane.
I know.
Yeah.
That we figured that out.
Isn't that crazy? Yeah. I'm like, it's just amazing. I know.
Yeah.
I kind of want to look at the history now.
A lot of times I make jokes about this with my students where I'm like, oh, back in the day, they had to do this. And I would not have been a chemist back then because that seems way harder. It's like, how do they I don't know how people are so smart that they
literally
figure things
so
out.
smart. Oh. And I'll say that's such a good segue into like my application, MRI
Wait,
applications.
can I ask you a question?
Yes, actually,
One more question.
No,
So,
all the questions.
For me also, when I'm doing NMR in the lab, I'm looking at like, okay, I'm going to look at these hydrogens to give me information about the molecule. I think what I'm understanding is y'all aren't looking to find information about the molecule, but you're just looking at the hydrogens in the whole environment. So it's like hydrogens or protons in this tissue.
Yes.
They act like this. So here's all the, like muscle tissue. And that's going to look slightly different than a tumor tissue or something.
Yes. Yeah.
So it's not like the computer is learning like what's every single molecule that's present here. It's like when I'm looking at the different ones, I'm like, oh, it must be in this type of bond. So it's going to act like this. And that tells me about the bond. But you're more like, it's in this type of environment. And that tells me about the environment.
Yes. It's like very structure based.
Okay.
Now there are applications where MRI can be used to like where you don't even really care about structure. There's something called like dynamic contrast enhanced MRI where you can look at the movement of fluids throughout a tissue structure kind of thing. So that doesn't really look at structure, but it's more about like what is going on in the environment versus like the actual molecule itself. Because think about like I just even taking the brain, like there's glucose, there's water, there's ions, there's all these sort of different things that it's like, whoa, like there's just a lot going on.
Yeah, I think that helped to bridge a gap that I've had for a long time because I've known how NMR works, but I have not understood what MRI was. I mean, I knew it was the same, but I didn't know how. And so that really bridges a gap of like, okay, we're not necessarily trying to find what's every single molecule in the body and then where is it and whatever. We're like saying all the glucose is acting like this. Or like, okay, all the gray matter is going to show up in this, thing so we can see where gray matter is versus white matter. And all the hydrogens in that are going to act roughly in the same way and give a signal that's consistent enough that we can group them together. That really helps me.
Yeah.
I've wondered for so long. I tell my students, I know it's the same technology, but I don't know how.
Yeah.
Sorry.
So it's like clinically MRI is used a lot for like just the identification of things. Yeah. So it's like for example, I tore my ACL 3 years ago and I had to get an MRI and they were able to see, like the ligament is not attached to her tibia anymore. Like it is torn.
Yeah.
And they're able to see because it's like, there's no tissue there anymore. It's just like a blank space.
Yeah.
Because in this MRI, the fluid was dark and the tissue was bright, like white. And so they're able to see that like, in a normal scan, I know that there's supposed to be like a little squiggly line here. Not a little, it's actually pretty big. But I know on your MRI, it's not there. So I know something happened. Or like I work in a stroke lab. So we'll do like a stroke model on rats, and then we'll do an MRI and we'll see that there's like just a big blot on their MRI, and we're like, okay, that's where the stroke happened here. It's because there's damage. So now there's all this water, like almost free water there, because there's all this damage to this tissue loss. So stuff like that. So that's really helpful. It's like clinically, that's like what MRI is really good for. Like for looking at tumors, and like what you said, it's like I don't have to open up somebody to look at it.
Right.
And I can just look at them live. Oh, isn't that so good? It's so fun.
This whole thing is very satisfying for me.
I just
Oh no! Mic drop.
I'll just be like a pad and
yeah. Okay, there we go. That should work. Okay. Yay. Okay. So, I just really like the research part of the MRI, because literally I feel like maybe I just like made up that my professor said this, but I feel like he said you can really do anything you want with the MRI within the limitations of the machine itself. But it's like if you can find like the parameters you need to look at what you want, like you can do it. And if it's like specific enough, and if like the signal will actually like, pop up, like I think you can do whatever you want. Unless you find that you can't, I guess, which doesn't mean you can do whatever you want. Anyway.
No, I know what you mean. It's like, it's incredibly powerful. There's so many options.
Yeah.
And as long as you are within the limitations of the thing, you can look at so much stuff.
Oh, yeah, for sure. Like you can like, I found a paper that somebody was looking at calcium using MRI. Like, so they just like tuned it to calcium, which I think is kind of crazy because it's an ion. But I don't like thinking the principle of it. I'm like, I don't know if it has like the spin and like the magnetic moment and stuff, but they found out a way to do it. And so it's like a specifically tuned to calcium. You can also like, they make special, like what we called coils. So like they make special coils that are specifically tuned for certain different, like we have a carbon 13 coil at my school. So that's always really, really cool. The one thing I'll bring up, like that I'll actually talk about, is functional MRI, because functional MRI is so cool. We have some people at my school that do research with it. So I'm really excited for like their data to come out and everything. So yeah, MRI is usually like in the clinic, like we usually get them, it's like one picture at one time, right? It's like only something like in one point of time. But we're not static. Like there's always processes going on. There's always something happening. So functional MRI actually can help measure things that are going on in real time.
Whoa.
It's really cool with functional MRI. It's a little convoluted, but I think I can do it. So when a specific part of your brain, it's a brain MRI. So when a specific part of your brain is active, it needs more energy, right? And so when it needs more energy, we use oxygen to make energy. To make glucose, you need oxygen as part of like the equation. And what brings oxygen to your tissues is blood, right? Well, like oxygenated blood, so when like hemoglobin, which is the protein that carries blood, has the oxygen in it, it behaves differently in the MRI than when it doesn't have an oxygen.
Oh, that makes so much sense.
Yes.
Because the chemical environment is different.
The chemical environment is different. So it's like, it's paramagnetic is what it's called, but you don't really need to remember that. So when the specific part of your brain is active, there'll be like a rush of blood into that part of your brain, and it brings oxygen into that specific part of the brain, so we can see what parts of the brain are active due to that.
Oh my
principle.
God.
So isn't that so cool?
Yes. And are they just taking like, is it like a movie where they're just like taking a bunch of like one right after another, basically?
Yes. So you can like take them in sequential order, and then you can loop them together as a movie. And a lot of papers will do that. They'll like have it in like the supplemental figures. They'll be like movie 1, and you can press play and it'll be like, here are the things. So it's like you can do so many things. You can make people do whatever you want them to do when they're inside the MRI. So like you just have their head inside the MRI, and they can like do things with their hands. Like they can click buttons. I know there's people that will do like tasks. Yeah, they'll just do tasks. And they'll look at like, oh, like how good are they when they switch tasks? Is that related? What part of their brain is active when they're switching tasks?
Yeah.
What part of their brain is it like? So I saw one where like they were watching a movie inside of an MRI. And then it was like it was a substance abuse. So like they were, they were watching a movie and then they were determining how like a drug like made them feel afterwards. Or it was a movie about someone like taking cocaine. They were like, does this make you want to take cocaine?
I see.
And they had people who were cocaine users and people who were non-cocaine users and seeing how that affected them. It was so interesting. So it's like they're literally inside an MRI. I think it was like a VR set almost. Like it's like the screen was like right here. And like they're just sitting there when the MRI is being taken, and it's like you're able to see what is going on.
That's crazy. Dang.
And I feel like that also bridges a gap between another part of my research, which is like I'm learning about how people learn, but it's more like, okay, the experience of learning almost, where that is like the physical, what is actually the neuroscience of like what's happening in your brain when you're learning. And so it's kind of cool to think like, I would love to see eventually being able to like watch what's happening in someone's brain when you're like doing chemistry, you know?
Now I saw I didn't click on the paper. I should have. I saw a crazy thing that was like, we're able to see what people see like in their brain, like in their mind, like what like they're able to like what they're seeing. Like it's like what their visual field is getting. We can like make an image of it using functional MRI. But I didn't click on it. So I don't know how true it is, because sometimes papers titles will be like, we did this crazy thing. And then you go and read it and you're like, you didn't really do the crazy thing. You just kind of did the crazy thing. Yeah. But anyway, so I'm like, functional MRI is so cool. I like, for example, one of the things we've like learned is that like there's a network in your brain that's activated when you're not doing anything. Like when your mind's wandering and when you're like just kind of like self-reflecting, you're like literally not doing any task. You're just sitting there. There is a thing that's active called the default mode network.
Whoa.
And we've only gotten to know that because of functional MRI. Because it's like, okay, just like get an MRI and don't do anything. Like you can let your mind wander, like just sit there. And it's like, no, there are parts of your brain that are active during that time.
Yeah.
Yeah. And it's like we were able to find that because of functional MRI.
So is that why we should be bored? It's like good to be bored.
Yeah. Yeah.
You got to let that part of your brain work.
Yeah, for sure.
Dude, that's crazy.
So cool. So, well, there was one more like fun fact that I want. Oh yeah, there's no radiation in MRI. So unlike X-ray, there is radiation. There's no radiation with MRI at all.
Nice.
So the safety thing that comes with MRI is that it is so magnetic. You cannot bring any metal into an MRI room.
Right.
Any metal, like people have been killed because they bring metals into the MRI room because the metal is so strong that it brings whatever you bring in that's metal.
Wow.
I think I found that clinical scanners are like 66,000 times stronger than the Earth's magnetic field. The MRI that I use that's in the basement of our school is 150,000 times stronger than Earth's magnetic field.
Oh my gosh.
But it's smaller, so it doesn't take up a whole room. It doesn't even take up half a room. I would say it's probably like the width of like 2 of these tables. So there's like a little safe zone. So like I still like bring my phone down there, but I just leave it in the room. Like I can bring it in the room, but I can't bring it around the scanner.
Yeah. Do you have the megahertz or whatever of your instrument?
It's Teslas is what it's measured in. So a clinical is usually 1.5 to 3 Teslas is like the strength of the magnetic field. We use a 7 Tesla. That's usually in research is what's used. It's because you can get more spatial temporal resolution the higher the magnetic field is. You're just getting better images. So it's just for clinical. You don't really. It's not like you're researching. You're not caring about specifics. You're just wanting to look at is something there or something not there. So you don't really need that strong of a magnet. And the stronger the magnet, like the bigger everything needs to be is. Yeah. And so that brings me another fun fact. One more thing. I just get so excited.
This is so fascinating.
I know.
Yeah, it really is.
So this is followed by one other fun fact that actually the world is running out of helium.
Well, we didn't talk about that.
We did talk about that.
Yeah.
Okay. Yeah. So that's connected. So like, what does that have to do with MRIs? Well, MRIs, because the magnet is so strong, it needs to be superconductive, which basically means it just needs to be at like really, really low temperatures. And how it is cooled is by liquid helium. So when we run out of helium, like that's really like, I remember hearing that and being like, who cares? Like the helium balloons will be gone. But it's like, no, we need them for the MRIs. Like actually, like we need them for the MRIs.
That's so crazy. We talked about, this was a long time ago, but Melissa talked about that like we're running out of it. And the use cases actually for stuff that really, really matters, not just the balloons, is actually surprising. There's a lot of things. Yeah. And so we should think about that when we're inhaling the helium and doing that. And
I think, listen, don't get mad, but I think it should be illegal to fill balloons with helium. When we're running out of it, we're running out of it, and we need it for things that are literally life-saving things, and we're using it so that kids have balloons that float. I mean, that's fun, but like, that's insane.
I know.
Is there something else we could fill the balloons with? I mean,
like balloons filled with air float. They don't float for as long, but like,
you could just make it to where it was less dense in there.
Mm-hmm.
Maybe you could fill it at a different temperature, so that then when it gets to room temperature, it's less dense in there.
Yeah. It has to overcome the weight of, I guess,
I mean,
but I'm like,
I think we could find things.
At the end of the day, we don't really need the balloons to float, is what y'all are saying.
Right.
So.
Because we need it for the MRIs.
You can use tape and stick them to the wall, and they'll look like they're floating.
Totally.
There you go. And like, who cares? Yeah. And that's like, and that's also another reason that like MRIs are always on a ground floor or a basement, because since they require all this helium, they have all these magnets and stuff. They're literally so heavy that they can like structurally in a building cannot be on like a third or fourth floor.
Right.
Yeah.
It's like,
because
you wouldn't have built.
Do that.
Yeah. A structural engineer is going to be like, no. We don't want.
Silly.
We're not going to build this fourth floor room so that it can hold this insanely heavy thing.
Yeah.
We have NMRs in the UNT chemistry building, and there's like areas where you can't go if you have a pacemaker. And like, you have to check before you go up and drop the sample in. And at the time, it just kind of seemed like no big deal. But in hindsight, you're like, oh, that's kind of crazy.
It's like a huge, like, again, like today I was actually at the MRI and I had my phone in my pocket and I was standing literally right next to it. And I was like, oh my gosh, that could have been really bad. But again, like there's like a safe zone for MRIs. The human MRIs are so big that the safe zone is like outside of the room.
Right.
But like it's a small mammal MRI. So it's specifically for rats and mice. The safe zone is like 2 feet outside of the MRI. So as long as you don't have anything magnet in that area, which is funny because we've also had magnets in there. But there's also like titanium and copper don't really matter because they're not magnetic metals. So there are MRI safe metals that you can use, but you just have to be careful. So like literally anytime you go to get an MRI, it's like check if you have like some metal implant, or like that's why you don't wear jewelry or anything, just in case. It's like that would be like things will like get ripped. Like if you had earrings in that were magnetic, they would get like ripped out of your ears. Like it's bad. So it's scary.
I have an uncle who had a stroke like probably 50 or more years ago, and he can't get MRIs because the technology that they used at the time was metal based, and they don't know what kind. I don't exactly remember what it was. Something they did that like an intervention after his stroke was like, okay, they put this thing in his body, and back then there was a time when it was metal. There's a time when it's not anymore. It was like safe, and he was right on the border, and they can't find documentation, and so it's like he's never gonna be able to get an MRI
ever.
Yeah, it's like you can't risk that.
Yeah,
wow, that's crazy.
So, it's pretty wild.
I know,
and it's wild to me that someone figured this out.
That's what I can't get past.
And somebody had to tell the computer what to do.
Yeah.
So that's my MRI story.
Well, that was so cool.
I know.
Gosh.
But really, it's just like the mind-blowing fact that like it's quantum mechanics, which is physics, of like an atomic nuclei, which is chemistry, to like diagnose and like look at biological structures, which is biology. So it's like all three of like the major like sciences. I guess it's not earth sciences, but that's about it. Like I mean, the Earth, magnets,
the Earth,
stuff.
So it's we're on Earth.
It's like all the sciences in one like experiment, and then just like people just do it every day, and it's like you don't even know how cool what's going on. So it's like next time you get an MRI, just think about all the protons in your body shooting up and then spinning back down, shooting up and spinning back down.
What's so funny too about you mentioning the different types, different sort of sciences or fields or whatever, is like, I don't know if you saw this, that on a couple of our shorts recently on YouTube, people commented like, is this chemistry or is this physics? And it's like, listen, everyone, we made up the boundaries because we're trying to have people specialize, but the world doesn't care. Like, it doesn't, it's like, it is chemistry and there's physics. Yes.
Yes.
And,
I saw like a meme one time that was like biology is just applied chemistry and chemistry is just applied physics. Physics is just applied mathematics. Mathematics is just applied philosophy. Like it just like kept going. So it was just like, it's all the same. It's all the same.
Yeah. And I'm like, listen, what is physics? It's about the movement of what?
Yeah.
What's that?
You gotta have stuff that is moving.
Yeah. So I'm like, or even wavelengths. It's like, that was somebody who was talking about it. Like, oh, well, isn't physics about like the movement of light or whatever? I'm like, yeah, but there's physical chemistry and like we talk about the way that energy interacts with molecules in chemistry. So,
Yeah.
And also we call it physical chemistry, but the things we talked about in physical chemistry, my husband talked about in his thermodynamics class.
Right. Yes. Yeah.
So you're like, okay, what really is the difference? It's just that engineers taught that one versus a physical chemist.
Yep. And you're going to end up being taught the amount of the thing that is going to be useful for the field you're going into. It's like, you're going to learn some of this, but it would be useless if you're going to go
all.
Build, design parts like what Mason does. There's an amount of this that's going to be useful to you.
Yeah.
And there's an amount that won't be. So
wow.
Sometimes he's a bad person to test stuff on because I'm like, did you know blah, blah, blah? And he's like, yeah. I'm like, engineers. And then I go to somebody else and I'm like, did you know blah, blah? And they're like, no. And I'm like, isn't that amazing? They're like, yeah. And they're like, oh, you're boring, Mason. So
I love that.
Well, thank you so much for teaching us,
Thank you for listening about MRIs and everything.
This bridged a gap that I've had in my mind literally since I was in college, and I've tried to figure it out, and it was never satifying. Yeah. And so having someone who has an expertise in this area was amazing.
I'm glad. That's all that matters.
Yes, super helpful, very cool, and just a crazy world that this whole deal is. So thanks for sharing with us.
Yeah.
You want me to start doing the wrap up stuff?
Yeah, I think we could wrap up.
If you have a question, thought, idea, follow up to this kind of stuff, that'd be awesome because it would give us a very good excuse to quickly get Claire back over here. But or about anything else that you think in your life might be chemistry related, please send it to us on our website at chemforyourlife.com. That's chemforyourlife.com to share thoughts and ideas with us. If you'd like to help us keep our show going and contribute to cover the cost of making it, you can do that on our Patreon. Join our super cool chem community of patrons on patreon.com/chemforyourlife. You get an ad-free feed of the show. You get bonus episode every month. You get some fun ways to hang with us and interact with us. And most importantly, you keep the show going. You keep it free for everybody else. And so we'd just like to say thank you. And you get the perks or bonuses, but we are just grateful because this show could not exist without our patrons. You can also grab some merch on our website at chemforyourlife.com/store. That's a great one-time way to support the show and, get some swag for yourself. And lastly, you can just help by subscribing to our favorite podcast app, writing a review on Apple Podcasts or Spotify or whatever app you use, subscribing on YouTube, leaving a comment over there saying hello. Those things help us to be found by others and help us explain the chemistry of their everyday life to them.
This episode of Chemistry for Your Life was created by me, Melissa Collini, her, Claire Caballero, and him, Jim Robinson. Jim is our audio engineer and made it sound so beautiful. Do we sound better than normal?
Well, there was some clipping that I'll have to figure out. So there might be a little bit of like, is he doing
his job?
Yeah.
If we sound different, it's because we've upgraded to higher quality mics so that we can sound more beautiful in your ears long term. So very exciting.
Well, especially sound more beautiful once we've tinkered with them a little bit. So be patient with us.
Yeah, right. Yeah. I mean, I always think it sounds amazing. So, and we of course want to give a special thanks to Claire and all of our amazing Patreons who made it possible for us to get this nice new equipment. And so we want to thank every single one of you by name. So thank you to Hunter, to Chris and Claire, to Steven, to Timothy, to Katrina, to Scott, to Vince, to Kyle. Thank you to Brian and Latila, Rachel, Elizabeth, John, Jesse, Doreen. Doreen, I tell my students about your hydrogen bridges all the time. Heather, Ash, Emily, Avishai, Chelsea, Christina, Jacob, Venus, Suzanne, Erica, Cullen, Jeanette, Autoclave, Julie, Justine, and Amanda. It's so exciting that list keeps getting longer. And we are so thankful to all of you that make this episode possible. Yay chemistry.
Yay chemistry.
Yay chemistry.
And yay Claire.
Yay me.
Yay me